Electric network elements. Renewable power generation. In this video, we'll talk about renewable power generation as part of the electric network. At the end of this video, you will be able to name various sources of renewable energy, know their characteristics, and compare them with each other. What is renewable energy? This term refers to types of energy that can be replaced naturally. This means that they have suitable characteristics and are constantly replenished. This video will provide insight into photovoltaics with the sun as a natural resource, wind energy conversion systems, hydropower and ocean energy using water as the resource, geothermal energy from the subsurface of the Earth, and biomass as a source of energy. In 2018, 33% of the European electricity generation came from renewable sources. While geothermal is not that significant, the highest share comes from wind, hydro and ocean generation, followed by biomass and PV. Photovoltaic or PV modules use the sun as a natural resource to generate electricity. Semiconductors are used as material for PV cells. These semiconductors are not conductive per se, which means that in the natural state, no electric current can flow through them. The reason is that electrons, the electric charge carriers, are located in the valence band and not in the conduction band. A current can only then flow when free electrons jump to the conduction band, which requires a certain amount of energy. This energy is emitted by the sun and is quantified by photons. One photon helps the electron to overcome the energy gap and to reach the conductive band. This is called internal photo effect. With a surplus of electrons in the conduction band, an electric field is created, which results in a voltage and, when connected, in a current. Photovoltaic cells and their output power can be influenced by shadowing, the sun's angle of incidence, and their direction. Shadowing reduces the output power, as sunbeams cannot reach the PV cell directly. The angle of incidence of the sunbeams, and hence the tilt of the PV cells, affects the power output as well. Optimal power output is reached for an angle of 90 degrees. Also, the direction and elevation of the PV cell influences the power output. Some photovoltaic systems even have an adjustable elevation and tilt angle in order to follow the changing position of the sun during the course of a day. Next, we're going to have a look at wind energy conversion systems, the influence of wind speed on the output power, and some differences of offshore and onshore generation. For understanding the connection between wind speed and output power, this diagram is helpful. It shows the output power versus the wind speed and marks the nominal power of the turbine. If we follow an increasing wind speed, we notice zero power until reaching the cut-in wind speed. From this point forward, the power output increases exponentially with rising wind speed until reaching the nominal or rated power, and hence the nominal wind speed. Now, an increase in wind speed does not result in an increase in power anymore, but once the cutout wind speed is reached, the turbine is shut off in order to prevent damages. In conclusion, wind turbines do not generate electricity for every wind speed value. Yet, for a certain range, the higher the wind speed, the more power can be produced. That is why there is strong interest in wind turbines installed offshore, where the average wind speed is usually higher. Additionally, these turbines usually have greater nominal power than onshore turbines, and thus are able to produce more electricity. On the other hand, the advantage of onshore wind parks is that they are less expensive and easier to maintain. In Europe, 10% of the installed wind capacity are offshore wind parks, and 90% of the installed capacity is onshore. Hydroelectric power plants use potential energy and natural elevation differences to generate electricity. Run-of-river power plants sees natural elevation differences of a flowing river. Using a weir, water is backed up and powers a turbine when released to the lower water level. This turbine is connected to a generator that converts kinetic energy into electrical energy. Storage power plants use the same principle. but the elevation difference is much higher as the water is stored behind a dam. Hence, more energy can be generated than with run-of-river power plants. Pumped storage power plants are not installed in a river, but create the elevation difference by pumping water from a lower level to a water reservoir at a higher elevation level. These power plants are mainly found in mountain regions. Besides the mentioned hydropower plants, energy can also be generated in the ocean. Tidal power plants are making use of tidal waves caused by the forces between the moon, the sun, and the earth. In regions with a high tidal hub, a dam creates elevation differences which are compensated by water flow during tide changes. These flows drive a turbine which is connected to a generator for electricity generation. A wave power plant utilizes the kinetic energy of moving waves. For example, a chamber system uses the water fluctuation caused by waves to compress and release air. This air flows through a turbine and is converted to electricity by a generator. Ocean current power plants can be found in regions with high ocean current speeds. Their working principle is related to wind turbines. Ocean current turbines are installed below the water's surface and harness the kinetic energy of the ocean currents. The usage of geothermal energy for electricity generation or heating purposes is possible in regions with thermal water existence. A hot water reservoir is reached by drilling and hot water is delivered to the surface. Using a heat exchanger, the heat is transferred to a power plant. Turbine and generator transform the heat into electricity and feed it into the network. The residual thermal energy can then be used for heating purposes and the remaining fluid is fed back to the reservoir. In 2018, 60% of the total geothermal energy in Europe was used as electricity. 33% were used for heating purposes. The term biomass summarizes organic and therefore carbon-containing materials. Biomass can be processed into liquid biofuels or biogas for energy generation, or it can be burned directly. Different types of biomass can be distinguished. Energy crops, for example corn or rape, are crops exclusively grown for energy purposes. Residues including, for example, straw, but also forest residual wood. Manure and industry residual wood are byproducts that can be used as biomass. Another possibility is to utilize some waste, for example, sewage sludge. Processing these primary energy carriers leads to solid, liquid, or gas products, the secondary energy carriers. Processing can involve drying, compressing, pelletizing, conversion to biogas, or fermentation to alcohol. Biomass power plants can transform the secondary energy carriers to electrical energy by burning them. These power plants often operate as combined heat and power units, but burning biomass solely for heating purposes is also very common. Biofuels do not have to be burned. They can also be used directly for transportation purposes. To conclude this chapter, different renewable technologies will be compared to each other to find similarities and differences. One characteristic is volatile and baseload suitable generation. Volatile generation, which is subject to more or less predictable fluctuations, is represented by PV and wind energy. On the contrary, hydro, ocean, geothermal, and biomass generation are either constant or can be scheduled, and thus become baseload suitable. Looking at electricity and heating purposes, PV, wind, hydro, and ocean energy only generate electricity. On the other hand, geothermal and biomass generation is able to produce both electricity and heating. The last characteristic evaluates whether the technology is bound to a specific location. Although the location has an influence on the energy output of nearly all mentioned technologies, in particular hydro, ocean, and geothermal generation are bound to a water or thermal resource. PV, wind, and biomass energy are more independent from the specific location. In conclusion, given these different characteristics, a combination and mix of all different technologies supports the success of the energy transition. Thanks for watching.